Good evening. I think we'll get started. My name is Cindy Passmore. I'm the chair of the Graduate Group in Education. I'd like to welcome you all to tonight's Distinguished Educational Thinker Series talk by Dr. Noah Finkelstein. This speaker series is sponsored by the School of Education, the Graduate Group of Education, the School of Education Alumni Annual Fund, and tonight's talk is also sponsored by the Division of Mathematical and Physical Sciences. Thank you for that support. I also want to announce that our next talk, Distinguished Educational Series talk, will be given by Dr. Barbara Rogoff on April 10th. So it's my pleasure to introduce tonight Dr. Noah Finkelstein from the University of Colorado at Boulder. He studies physics education and is an educator focused on STEM education reform, and particularly at the undergraduate level. He's the co-director of the STEM Learning Center there at Boulder that's getting started, and is a national leader in coordinating such centers across the country and trying to get some movement going on STEM education research on a broad national scale. He's been the recipient of many honors and many NSF grants and awards, and in particular, he's received many teaching awards. So we'll look forward to seeing his prowess tonight during his talk. In addition to his research and teaching, Dr. Finkelstein also serves in an advocacy role for education on a national level. He serves on several national advisory boards. Most recently, he's finished a stint as chair of the Education Committee for the American Physical Society, and he serves on a technical advisory board for the AAU STEM Education Initiative. So without any further talk by me, I will introduce you to the person you came to see, Dr. Noah Finkelstein.
What a pleasure it is. I assume you can all hear me. Otherwise, I'll use my teacher voice. It's such a tremendous pleasure to be here. I have long-standing admiration for the University of California, Davis. About half of my high school class came here as I grew up in the Bay Area. Very strong commitment to the Ags, and I've been following the tremendous work that's been going on here for decades and decades in STEM education. And I'm totally flattered now to be in a similar speaker series as my friend Barbara Rogoff. I know I'm in the right place, so I'm very honored. In terms of my teaching prowess, I will not be giving any tests, nor will I be giving any candy, which is my real secret to my highest teacher evaluations on campus. But I do want to engage in a discussion with you all, and so I want to take the time here to make some meaning around education, to take a look at the large-scale national landscape that's going on, to take a look at what's going on in the ground, how it is that we can and in fact must all be involved in educational practice that's taking place in the transformations that sit before us. So just by way of understanding you all a little bit better, can I get a quick show of hands? How many of you are students currently? Yes! First off, I assume that's because you're already getting credit for it, but thank you so much for coming here. How many of you would identify yourself as educators or the School of Education? Wonderful. Science, math, engineering folks, practicing folks? Wonderful. Oh. Other areas? Filmers? Thank you. So, great. Well, first off, you're already a success. Congratulations. Cindy and to the deans, thank you so much for hosting me here. This is already a success to create a space and a dialogue of tremendous constituent communities, and I'm thrilled. So I'm very much in an interdisciplinary area myself. I'm housed in a physics department. I was mentioning before, I'm a member of what I believe may be the largest research group in physics education housed in the Department of Physics. I highlight that we have many faculty here, and particularly Valerie Otero actually is in the School of Education, a member of our research group, so we span between physics and the School of Education here. But we have a tremendous number, gaggle of postdocs and grad students, and we are part of a larger effort on our campus, and these are the members of our discipline-based education research community on our campus, which is really just remarkable that we have a weekly series where we get to have some of these interdisciplinary dialogues. And we're thrilled that, like you, we are now in the midst of establishing the Center for STEM Learning, which serves as a hub, like your IM STEM hub, for coordinating and collaborating. So let me start by asking a question. Maybe we'll start with one of the students here, if you don't mind my picking on you all. I'm sure we have some great Boulder swag in it for you. Why education? Why does our society invest $1 trillion a year in formal educational enterprises? Doesn't have to be a student. Yes?
To stay competitive with everyone else.
To stay competitive. In fact, this is the national charge in what we'll see here for what led to the Rising Above the Gathering Storm report from the National Academies. Charge from Congress was, what are the top 10 action items? Well, I won't give away the other ones. So, to stay competitive and secure were the two charges. Other ideas? No?
Participation in democratic, civic.
Participation in a democratic and civic society. I am back home in California. Thank you. That is awesome. We live in a society that is a democracy, but it's not just any kind of democracy. This is a representative democracy, but a democracy that's founded and grounded in the roots of an educated and informed citizenry. If we want people to participate, we have to teach them how to participate and to give them the tools in order to make choices that are incredibly important right now. Other ideas? Yeah?
Because learning is personally enjoyable.
Because learning is personally, now I'm definitely in California, if not Boulder, Colorado, you make me feel at home. There's a personal satisfaction and reward to this. And so, in fact, my priority order is in the exact inverse of what you all just said. I think individual empowerment. This is incredibly important. This is how and why we can engage. Societal empowerment. And this includes this idea of an informed and educated citizenry to engage. And then, of course, the national rhetoric that's driving education right now is workforce and economic development. And I think all of these are incredibly important. And if we only focus on one, careful what you wish for. So what will 45 minutes get us? Hopefully some time to talk about the national need and the context in which I'm working, and we are all working. Discipline-based education research is a key tool for educational transformation. If you'd like, a few key studies from the University of Colorado, where I'm so pleased to be working, how we can all build on these results collectively and engage, and then finally some discussion. So as I see it, we are living in, especially for you students, unprecedented times in your lifetime, and maybe unprecedented times in all of our lifetime. We have not seen the attention that's being paid to science, technology, engineering, and math education that we do now, certainly not since Sputnik and maybe ever in the United States. Sputnik for you students, there's a satellite that was launched. All right, so what are the grand challenges that face us? You may see this. This is the rhetoric. This is, I assume these are going to be the data that Obama talks about tomorrow night in the State of the Union. That the U.S. is not competitive, that we rank 21st and 25th in math and science education. These are data from PISA that are recently reaffirmed. And we can talk about this, about whether or not competitiveness with the rest of the world is the right goal, but certainly for being a leading industrialized country and having the resources that we do, we shouldn't be sitting in the bottom of the barrel here in terms of our educational performance. And if you want, we can chat about this in Q&A about where we sit either. These data hold out to be incredibly robust, not only for 15-year-olds, but for, well, at many different levels. We can talk about that. This is related to the fact that we need more and better teachers. If any of you students here are thinking about going into teaching, I highly encourage you. There's no more noble profession. There's no more personally rewarding profession. And it's an area of tremendous societal need. In physics, there's no area of greater need than in physics. Chemistry and mathematics are always vying for that other spot, this spot. 2 out of 3 high school physics teachers in the United States has neither a major nor a minor in physics. I was arguing to Arnie Duncan, he's our Secretary for Education, not too long ago, that one of the challenges with this is that teacher recruitment and preparation begins in freshman physics. And it's historically always been that way, and historically it's been for the worse. We've not been recruiting our students from freshman physics to go engage in this form of enterprise. We need more and better students in with undergraduate degrees in science, technology, engineering, and math. A recent study out of Georgetown, it's actually now 3 years old, suggested that we need 1 million more graduates in STEM by the year 2018. This is from the Center of Workforce and Education out of Georgetown, and they break it out by different disciplines. This is what's largely been taken up by the workforce argument, these data and arguments, and I argue that at the same time, our goal should be equality of life for all, and this is a fundamental form of infrastructure for our society, that this is why we engage in higher education. This is what a bachelor's degree does for you. And certainly in higher education, that the U.S. has been surpassed both by Europe and by Asia, actually quite a while ago now, in our achievements here at the PhD level and at the undergraduate level and at the master's level here. So we can talk about numbers and statistics if you like. So the question is, here's the argument as to, so these are the data. We can interpret what those data mean and why they matter. To begin, we might actually ask where this comes from, and if you're interested, I would argue that this is a result of poor policy. If you would like, I'm happy to play a clip later from Senate Majority Leader Trent Lott from about 15 years ago, which is when we're setting some of the seeds of this. So again, during Q&A, if any of you students want to remember, more swag in it for you if you ask for the video. But this isn't just historical. These data, the American Physical Society, my professional society, had to fight very hard to prevent 13 universities from shutting down their physics departments at universities. And just today, the Chronicle of Higher Education was asking the question, is a University of Texas degree worth it? Is a Cadillac of education needed anymore? So, this is an era of significant attention. This is an era of attention from the National Academies. I had mentioned before, in answer to your question, the Rising Above the Gathering Storm, for you students, the National Academies, I call them the Center for Smart People, is established by Abraham Lincoln. Did 4 tremendous acts during a time of war. So don't ever let politicians off the hook from doing a good thing. Well, period. That's just a good message anyway. So in addition to establishing and signing the Morrill Act, which established the land-grant university system and hence then the public school system, the public university system, which I'm very proud to be a part of, as you all, established the National Academies. National Academies charged from Congress, what are the top 10 action items for a competitive and secure United States for the 21st century? They came back with 4. Number 1 recommendation in priority order, 10,000 teachers, 10 million minds. This is where this started getting codified in our language. Of course, 5 years later, Rising Above the Gathering Storm 2, the follow-up study, rapidly approaching Category 5. This is in reference to Katrina. The National Academies subsequently created these frameworks. It may be for the first time in the history of the United States that we have enacted national standards in science. It would be a tremendous move for us, especially if we're able to support them in ways that are needed. The National Academies last summer issued the Discipline-Based Education Research Report, the scholarly report looking at the nature of educational research in-house, in disciplines, and I'll talk about why that matters, and I'm very proud that the Board on Physics and Astronomy is issuing this so-called decadal study, a 10-year look forward and backwards in physics education and physics education research within the United States. It's an era of attention from the United States. This is the America Competes Act. This was the act that, for those of you who are in graduate school, really seeded the doubling to tripling of the number of graduate research fellowships and really started pushing some of the 100,000 teachers in 10 years. This shows up in the federal budgets. I also assume that this will show up in the White House speech. There are 2 great reports out of the President's Council for Advising on Science and Technology, and this is the more recent one. Again, take a look at this. Here it's the Engage to Excel, producing 1 million additional college graduates. Where do you think that number 1 million came from? It came from that earlier Georgetown report. This is being enacted now in national policy. And I'm thrilled that the National Science Foundation is deeply getting in this game to try and understand this widening implementation and demonstration of educational reforms efforts. I hope this is a tool that takes root, because it can be an instrumental tool for universities to engage and transform. This is my major theme here, is that universities can step up and participate at the table in educational transform. I'll hit this point a little bit more in a moment. Professional societies are engaging in unprecedented ways. It was mentioned that I'm on the technical advisory board for this initiative. The Association of American Universities, the lead 62 research universities, so the Harvards, Yales, Princetons, Colorados of the world, who are engaged in research, their major educational initiative now, their first major educational initiative is in STEM education reform. Similarly, the largest coalition of universities, the Association of Public and Land-Grant Universities, their major educational initiative is a science and math teacher imperative. Notice the word imperative. They're sort of engaged in all of this. And again, my own professional society, the American Physical Society, I'm thrilled that they have efforts for, this is one of the largest networks of teacher recruitment and preparation in the United States. 250 universities are participating in Physics Teacher Education Coalition. Physics departments, 1/3 of all physics departments in the United States now say teacher recruitment and preparation is part of our core identity. And of course, I was thrilled to be able to institute an award from the American Physical Society focusing on undergraduate education. This year, MIT won it along with Colorado School of Mines. Next year, it should be Davis. We have a graduate education conference that just met, focusing on this, and the one professional society that's represented in the PCAST report that's heralded is the American Physical Society and American Institute of Physics for their new faculty workshops that are models for educational change. So why do I talk about all of this? Why is it that I talk about professional societies engaging in this, the National Academies and the White House? And the answer is, we have tremendous potential to bring to bear the university system in educational transformation. The federal government is the largest driver of education in the United States right now. That it's this major endeavor, a $1 trillion a year enterprise, right? So that's pretty big. So we have race to the top, $4.5 billion. That's a lot of money, but not when you compare it to $1 trillion. You can't hit these systems head on, so the federal government is engaged in using levers of transformation. And the two key levers that the federal government, have any of you heard of No Child Left Behind? Many of you perhaps are the product, or you're still talking to your therapists about No Child Left Behind. So No Child Left Behind was really a move to shift national policy. So policy is a key lever in this. This is what Race to the Top was about too, was to try and invest in getting states to shift their legislation and policy practices around that. So it's a key lever in change. The other key lever that the federal government has been bringing to bear has been industry. Change the equation. It's the industry leaders. This is why you see Phil Mickelson hitting a golf club saying, math and science is important. Sponsored by ExxonMobil, who invested $350 million in educational transformation through their National Math Science Initiative program. I think incredibly important. Intel's getting in the game. Of course, Microsoft, you've heard of, very much in the game. A key and untapped lever in educational transformation in the United States is education itself, and in particular, higher education. That we have a responsibility and an opportunity to step up and participate at the table. I show this picture here because it's my office. This is where I get to live. But the universities represent a tremendous, we could not ask for better infrastructure for us to engage in. It's geographic, universities are already geographically distributed, so if we want to have regional impact, most teachers teach near where they were certified, at least in physics, but I believe this is true nationally as well. So we have regional focus and regional content. But universities are where we're recruiting and preparing the next generation of teachers. Universities are where current teachers return for professional development, or should. Universities are where we're educating an increasing fraction of the United States. More and more students in the United States are going to university, and it's more and more demanded of students to have a bachelor's degree. We're the ones who are defining what science, math, and engineering are in practice. We're the ones who are creating this. We're also the ones who should be setting the standards. What are the standards? What are the assessments? What are the kinds of pedagogical practices? And this is why I'm thrilled that there's such opportunity and such attention now to discipline-based education research and my own field, physics education research. I'm going to talk a little bit sort of from home now. Are there any immediate questions? How many of you are familiar with what physics education research is? Okay, so some fraction of you all. So it's this field that's grown up, and it happens in many fields. When I use discipline-based education research, this is education research that takes place in-house, within disciplines, or on disciplines very specifically, so that there is now opportunity for us to have a focus on not just how is it that students are learning, but how is it that students are learning this physics that we're teaching here at Davis in these environments. And there's this tremendous opportunity to partner between the tremendous knowledge and work that's going on in schools of education. We cannot do the work that we do without the great work in the School of Education. And at the same time, we need to have work that goes on in-house. I don't know if anybody has told the physics department this, but I suspect that they won't listen to the provost telling them what to do, or the School of Education telling them what to do, or anybody else telling them what to do. And you can correct me if I'm wrong, but certainly in Colorado, this is the story. So what we can do is in-house import a great and contextualized knowledge of how it is that we engage in practice. So this is a plot demonstrating that in fact we're not teaching our students. This is famed from 1998. Richard Haight, a professor at Indiana, showed that this is a histogram plot on the left axis versus learning gain. Learning gain is defined by this post-test, how well students scored on this conceptual survey of the most basic ideas in introductory physics. I have two objects, heavy object and a light object. I let them drop down. Which one hits the ground first? Heavy object, light object. Do they hit at the same time? Does it depend? They hit at the same time. That's right. Okay. So perfect learning game so far. So anyway, we can ask that at the beginning of the term and at the end of the term and call that difference learning. I also want to emphasize that's not learning. That's a proxy for learning. That's performance, how well students are bubbling out on a sheet. But hopefully this is being a research-based instrument, tells us what it is that students are doing. And already we've made huge gains over what we've already done in our introductory physics class, because now we're measuring what the impact is of what we do, rather than where is it that students are at the end of the semester, and how do they feel about it. So if my faculty ask me, did your students learn? I can say yes. At least in terms of these conceptual measures, I can see this. And then I divide by what they could have learned. 100 minus the pretest allows me to compare places where students learn a lot, like the University of Colorado, with places where they don't learn so much, Harvard. So, so this is a histogram plot, and you'll notice this is not so much learning over here, and lots of learning over here, and you'll notice something. Not so many classes over in the lots of learning category. In fact, the national data that have been replicated time and time and time and time and time and time again, like any good scientific enterprise, demonstrate that students learn about 1 in 4 of the most basic concepts in introductory physics that they don't already know as a result of our traditional forms of instruction. And we say that's sufficient. But it's not. So people have come along and say, what is it that we can do? The answer is we can engage students, we can challenge them, we can conduct work like the Physics 7 project here and get students wrestling with ideas and talking with one another. We can get them engaged and we can get them to interact. We can have them participate in classes. And as a result of that, you'll see, and these are data again from quite a while ago, 1996, for interactive classes you'll see these two things that you'll notice from this plot. Right? What's one of them? What?
There are bigger gains.
There are bigger gains. So just about any form of interactive engagement is as good as the best form of traditional lecture. So I'm a huge fan of John Taylor. He's a national award-winning physics instructor at the University of Colorado. He has a brilliant British accent, and I love listening to him. He ended up here because he lectured. Even the most novice educator, instructor, professor in introductory physics who engages the students, who challenges the students and has them wrestle with these materials, they'll do as well. And the second thing you'll notice is there's a huge variation here. How we teach seems to matter. How we teach students seem to matter. What it is that we have them doing. It's as though the teachers matter. It's as though this is a professional activity, and what we have people doing and how we do it matter. So physics education research has gone beyond this. It's actually taken a look at things like attitudes and beliefs. And what I mean by attitudes and beliefs is not end-of-term evaluations, which I do value. I really value whether or not people enjoy the experience. But we're looking at what Joe Reddish, my colleague at Maryland, has referred to as the hidden curriculum. Beliefs about physics and the nature of learning physics. So we have students at the beginning and end of semester answer questions like, agree or disagree with the following statement. I study physics to learn knowledge that will be useful in my life. is physics personally relevant to me? What do I think about the nature of physics? And to learn physics, I need only memorize solutions to sample problems. Do you want your students to agree to this or disagree to this? Depends, right. So, what's really remarkable is we get students who have been very well schooled at schooling, who have learned to be expert students. So you could imagine students come after some 16 years of schooling, perhaps, 14 years of schooling, and it's hard to impact these ways of thinking about the world. So it's really good news. We created this Colorado Learning Attitudes About Science Survey, or CLASS, and we look at students' connection to the real world, their personal interest, the role of mathematics in physics understanding. And what's really promising is that we could impact students' beliefs about the nature of physics and the nature of learning physics. The downside is that even for a reform-based class where there was a lot of that conceptual learning, they all shifted negatively. So my students walk out of the introductory physics class thinking that physics, a study of the real world, has less to do with the real world than when they entered the class. And I taught them this. I didn't mean to teach them this. This is the hidden curriculum. But sure enough, I taught them this. This wasn't intentional. It was unfortunate. It is unfortunate. And this is the staple in our classes. Unless we pay attention to the nature of learning and the nature of the discipline itself in-house, we're teaching students generally to think that it's less relevant, less meaningful. We have some great research now on gender disparities, and it's differentially impactful for non-dominant communities in physics, that's women and underrepresented minorities. But it's bad for everybody. So my research happens to be on examining the how and the why. I focus a lot on the nature of context in student learning. And I'll talk just a little bit about this because I think this matters so much to have a little bit of what I call a toy model or a proto-theory, a toy theory of education, because so much of our national discourse is around the following model of education, which is you can take content, you can take information, and you can deliver it via instruction to students. And that shows up, it's often dubbed as a traditional transmissionist model, but it is so common that people talk about educational delivery. It is so common that it is built into the structure of our classrooms. That we build our classrooms, we build our classrooms to engage in an educational practice that supports a theory of education that looks something like this. That there's something akin to green glue that is sitting here and dropping into the heads of our students as they're on a conveyor belt, passing through. And while I quip about this, and while I callously steal Bill Waterston's copywritten work to make his point here more public, if we're not careful, this will be embedded in the forms of education of the future. If we think that education is only about the delivery of information, it'll be put entirely online, and you will be getting your information from YouTube or the next generation of that. Careful what you wish for. I'm not a Luddite, I'm not anti-technology, I'm a physicist for crying out loud. We invented the web, not Al Gore. So we are technologists, but we are also thoughtful technologists. Here. So we know, of course, from great work in education and psychology that this is the underpinning, that people have to be engaged. This is this bidirectional arrow, that this is what it means to have your colored cards in your classroom, or your clickers, or turn to your neighbor and discuss things, or externalize your reasoning. This is this active construction, that interactive engagement that supports the data. And this, of course, comes from Piaget as this constructivist model of education. And we must make sure that we build in the physical spaces for that. But not only do we build on our prior understanding to make sense of the world, it's not just us and the world. We engage in the world by using, get this, humans are tool users. We engage in the world bringing a much greater suite of understanding, not just prior knowledge, but attitudes and beliefs, my own personal background, cultural background, affective issues. Maybe I'm good at doing it, maybe I know a lot about it, but maybe I hate it. And that's going to dramatically impact whether or not I engage with learning about electricity and magnetism, which is the ENM over there. And I do that by mediating through the uses of tools. I'll talk a little bit about what that means. And it also, all of this happens, our understanding and nature of understanding of tools happens in context. This is my research here, but we might just ask, let's think a little bit about tools. How many people do you suppose pull this door? Right? So tools, and whether physics is, physics is a tool just as this door handle is a tool, they're both human constructions, but you can imagine creating a different door handle that might be more effective towards those ends here. So well-designed tools lead to the their naturally intended use. And so my toy theoretic framework, this is the research that I do and engage in, and I think that it matters so much, is that tools mediate our understanding in cognitive processes. Tools allow for us to think, and I'll tell you a little bit more about what I mean by that, not a whole lot more. And then context shapes what I mean by tools. What's this middle symbol? Well, it can't be two things, can it? Right. So tools allow for thought. Sensitive a little bit to time here, I'll give you just a quick math example. I'll give you two math examples. So one, 7,960 divided by 10. Again, one of the students, please. Okay. Good job. That was easy. Okay. Now, 7,960 divided by 16. Okay, well that's harder. Right? Why is this harder? Why was the first one so easy?
Because we use base 10.
Because we use base 10. Why do we have base 10?
We have 10 fingers.
Because you have 10 fingers. But you could imagine we live in a different world. You could imagine a different world where we're organized a little bit differently, right? It'd make texting a whole lot easier, but it'd also make this problem easier because it would be in hexadecimal. And all of a sudden now it would be divided by 1 0, which, for those of you who know hexadecimal, is 16. And all of a sudden this problem becomes easy again. Now what I've done is I've shifted the tools that we're using. I've shifted the conceptual register here. But that isn't it alone. The meaning of these tools, I argue, is both biological, which is, this is an example of Shepard's tables here. And I can ask you, which one of these sides is longer? They're the same. You know that because you've been in school. You're well schooled. Right. But you know that they don't look the same. It's the same with the moon on the horizon. This is a slightly different illusion. This is a Ponzo illusion. The moon on the horizon looks big, right? And smaller when it gets up in the sky, right? Contrary to popular belief, the moon does not change size. Right? It has to do with perspective and how we see things as human, how we are biologically evolved. You can't build these tables physically, but these are the same size. So take a look at the Shepard's tables if you want. But then here's a question for the mathematicians and scientists in the audience. It's also cultural. So if I have, this is taken from work of Corinne Minot, if I have a function of x and y that's equal to a constant times the quantity x squared plus y squared, what's t of r theta? Not a trick question. Well, it is a trick question, but it's not a trick answer. Okay. Anyone? Come on, somebody's got everything. Yeah, it's the obvious. Okay, I think I've heard two answers. I heard the answer is c times r squared, and I also heard that it's c times the quantity r squared plus theta squared. And the answer is yes. Physicists say that it's c times r squared because you engage in this Cartesian coordinate shift. There's a shift from the Cartesian coordinate system to the spherical system here. So r squared is equal to the square root of, well, r is equal to the square root of x squared plus y squared, right? Familiar with different systems here? Thank you. But the mathematician says, no, this is an indexing problem, that I'm going to take this r here that's in the first spot and substitute it for the x that's in the first spot, and the theta and substitute it for the y that's in the second spot. So you get c times the quantity r squared plus theta squared. So then the dean of natural sciences said, you can't add meters squared and radians squared. You're not allowed to do that. And the mathematicians say, what's a meter? These letters take on different meaning to different people. These tools take on different meaning to people because of different context that we're in, different cultural backgrounds and different systems. And we take so much of this for granted in our educational system. I'll give you a very brief tour, I think. How much time do I have? Okay, I'll give you a brief tour of one of our initial educational innovations and transformations here that really focuses on this idea of context and recontextualizing the nature of education in a very real world way. So these are the tutorials in introductory physics that we implemented in our Physics 1 sequence. This is a calculus-based sequence. It's a first semester sequence. It's akin to the Physics 9 sequence here for those who are following. And we took the 1 hour recitation section, sort of the lab section that you all have, and we not so secretly replaced it with the most research-based materials in introductory physics. These have been around for a long time. They're out of the University of Washington. And these tutorials, they're worksheets here, but they're very thoroughly researched, and we conceived both materials and the classroom format and interaction and the instructional role. So we've gone from an environment that looked sort of like this, where there was one TA who would be sitting here and working at the board, and somebody would call it a number, 7, I'll work 7, and the students would dutifully transcribe that brilliant handwriting down onto their piece of paper, and we would then be teaching students to be tremendous stenographers. And we changed that classroom format now to look a lot more like what you see again in sort of the new Physics 7 labs and the great new building that you all have here, where the students are focused on tables here and pointed at each other. And you'll notice that in one environment, students are working individually on pieces of paper, and in another, they're working in collective, forcing them to interact and to engage, rather than simply to transcribe. The other thing you'll notice is that we have not one instructor, but 2, and they're happy. And the way we are able to afford that is, and that's at the suggestion of the curricular authors, the University of Washington authors said you need 2 people in this environment to really engage students. And the way we did that is the Colorado Learning Assistant model. And this is an experiential learning program and teacher preparation program, led really by my colleague Valerie Otero, though we all work very hard on this. And what we do is we take large-scale enrollment environments like that, and we make them look a little bit more like this. And the students are now working on real-world physics problems, sense-making and engaging here. And these learning assistants are the pool from which we recruit the next generation of K-12 teachers. We use these undergraduate students who are highly talented and recruited and then very well supported. They're not undergraduate teaching assistants. They're undergraduate learning assistants. They are paid. They are supported as part of their education then as well to help us interact with the students, to improve the education of all students, to increase the likelihood that students engage in teaching, and to implement our materials. And we can also demonstrate, well, I'll give you some demonstration. So what's really remarkable about this is, here are some data. Look at this. This is from before some of you were born, these data. The University of Washington, this is what convinced us to engage in this enterprise, is that the University of Washington looked at student performance. This is percent correct on the left axis, and then clusters of questions around 4 key areas of Newtonian mechanics, introductory mechanics, physics here. And they found that after lecture performance, brilliant lecture, and after traditional recitation where students work at the board, students would perform this well on these clusters of questions, particularly not well around Newton's third law questions here. And then they convinced us to implement this because they showed that after instruction using the tutorials, the students perform much better on these series of conceptual questions. These data are from 1981. So 30 years and 1,000 miles later, we find the following results at the University of Colorado. Stunning replication. This is one of the, and these are some of many sets of data that we have to demonstrate that education is a scholarly and reproducible act when appropriately conducted. If we treat this as a scholarly and professional activity, we can get reproducible data. We can understand why it does work and why it doesn't work. I mentioned to you those attitudes and beliefs. This is the C-last pre-post shift, and I apologize here, now this is a shift here. This is for a traditional class here with high learning gains. So students learned a lot, and these are all negative shifts. These are the same data that I showed you before, broken out male and female, in 4 different categories. And with some modest attention, if we made this hidden curriculum not so hidden, we found shifts. Well, they were not all that distinguishable from zero. First principle of educational practice, do no harm. Right? Don't beat the interest, identity, and association of learning out of students. And there are a couple of instances now that we've known since then about how to improve students' attitudes and beliefs. You can chat about that if you're interested. So Steve Pollack has really spearheaded this effort here, and we found that every time we've offered an interactive lecture, but a traditional recitation section, students have landed in this band. So our lectures are interactive. We use clickers, cards, and all the rest of it. But every time we've implemented this with learning assistants and tutorials, we've ended up in this much higher band. Ending up with learning gains as much as 3 times the national average for non-transformed classes. For a sales pitch, we say, come to the University of Colorado, you can learn 3 times more than you can elsewhere in introductory physics. It brings them in hordes. These data last. I think I'll skip through this, but if you want, I can talk to you about longitudinal studies here that we have. And I'll just run through. So this is junior year. And junior year, we had some students who only had a traditional freshman experience and some students who had a transformed freshman experience. So 2 years later, how is it the students are performing? And so this is one class. The classes on the left side here, fall 2004-2005, are for students who only had the transformed class, only had a traditional freshman experience. But by 2006 and 2007, students started matriculating into this environment who had tutorials in their freshman year. So the only difference, these students are in the same class as their junior year, but they're performing better in their junior year based on their freshman year experience. And those students who've been learning assistants, they perform the best, and in fact, have higher GPAs. We've recruited, this is a plot that I show our regents. I try and keep it very simple, before, after. We have more students who are entering our teacher certification program because we're recruiting them starting in our freshman year in physics. And especially in areas of high needs, right? We've had an infinite game of the number of students who are going into chemistry teaching. 1/3 of a student, it's very painful, used to go into physics teaching. Now we have actually well more than 3, we have 5 a year. Zero old data. We can also demonstrate, and I won't get into this, we can demonstrate by going and looking at the, this is Kara Gray's work with Valerie Otero. We can demonstrate using the Reformed Teaching Observation Protocol the practices of students who had been learning assistants once they go into teaching in the K-12 system. So if you had been a learning assistant and you go through the same certification program, when you're a teacher, you engage in preferable practices here in a whole slew of areas in math and science teaching. Okay, well, so I think I will skip it. I can tell you, if you want, during Q&A, we can talk about upper division transformation. We can talk about the role and choices that teachers make in practice. I can talk to you about institutional transformation, if you want to know about models and theories of transformation, because just like we can make scholarly inquiry and practice into the nature of educational practice in a classroom, we can make an inquiry and scholarly practice of institutional transformation. I can also tell you about our STEM Education Center, our Center for STEM Learning, that is applying all of these ideas. But let me wrap up here. So in physics, you'll recognize our standard model, which is now out of date since we found the Higgs, but physicists are a fan of having a standard model. How does everything work in the universe? Here, we don't have one, but we do have tremendous understanding about knowing about how students achieve in our classes, how to construct classroom environments, that are supportive of students, how faculty use these tools and how faculty can learn in practice, course tools and practices, departmental choices that we make, and in fact institutional choices that we make here. And I'm really pleased, I'll end as I began here by recognizing that having disciplinary faculty at the table in partnership with School of Education here, in partnership with the administration is essential. So when I mentioned to you this national frameworks, this was Helen Quinn, a physicist, retired from Stanford Linear Accelerator, who chaired this report. And when we talk about the America Competes Act, not only did I work on it, but our secretary recently stepped down, or about to step down, Secretary of Energy and physicist and Nobel laureate Steve Chu. When we talk about the presidential budget in the White House, this is the work particularly of Carl Wyman and John Holdren, both physicists in the Office of Science. Here, when we talk about the Association of American Universities initiative before, PCAS member Jim Gates, a physicist, instrumental in engaging in this. We talk about the Science and Math Teacher Imperative. This is spearheaded at the Association of Public and Land-Grant Universities by engineer Howard Gobstein. The Board of Physics and Astronomy report that I mentioned before is led by Don Langenberg, a physicist and former chancellor of the University of Maryland. And this discipline-based education report is led by Susan Singer, who's a biologist at Carleton College, now at National Science Foundation. American Physical Society has a physicist, Ted Hodak, leading their education efforts. And even in Congress, the American Physical Society's Public Policy Committee, Vern Ehlers, a physicist, now recently retired from this Public Policy Committee, but chaired this for several years, engaging in this. So the folks who are engaged in the disciplines must step up and must participate. And in fact, we already are. We're acting where it matters most, which is inside the classroom. This is my buddy Mike Gubson, as we teach in our introductory sequence. And he's a tremendous role model to many of us here. And we're operating not just at the individual course level, we're operating at the departmental level, and we're operating at the campus level. And we have the good fortune to not stop at the campus level. This is spreading across the country. As I mentioned, 250 departments are members of the BizTech Coalition, and now some 144 are members of the Science and Math Teacher Imperative. I think that this is, again, an imperative and an opportunity for us to all engage. Thank you very much. Are there any questions? Thank you. In the back. Please.
Yeah, so I'm a biology undergrad, and I did the physics studies, and I thought it was great. I thought it was a lot more fun than lecture, and I felt like I learned a lot, and it was a really just a great environment for learning. I felt that. But people seem to hate it, and I hear nothing good ever about the Physics 7 series, and people feel like it's a waste of time, and it's just inefficient, and why are we sitting here trying to solve it? Why don't we just learn it? So what do you think that could be done to sort of shift the attitude among students?
So to summarize and maybe repeat the question, let me know if I get this wrong. I'm a biophysics chemistry major. I took Physics 7. I loved it. Other people hate it. That's what we hear. Is that true, and what is it that we can do to sort of shift attitudes? My understanding is that people are split on this, and we are violating historic norms, both for the students and for the faculty. Again, I think that most people, and I think in the United States, we suffer from to be political about this limited theory of education. If we think about education as information delivery, then yes, this is inefficient. This is an inefficient form of information delivery. But we're not in an information-limited society. We haven't been since the creation of the book. That's a B-O-O-K, not an M-O-O-C, for those of you who follow. Right? So the book, I mean, and certainly since Google, we're not in an information-limited society. People have access to information. What they don't have access to is knowledge. They don't have the organization of information. They don't have the access to know when and how to ask questions. And so I am a fan of lecturing. I think that lecturing is a key tool and can do tremendous things. It's partly what I'm engaged in here. And it can serve as a key purpose for things like cognitive modeling. but it is way overused. We're way saturated on this, and there are lots of different psychological studies that say people lose their attention span. There are about 6 of you who are asleep in the back, which if I were in my classroom, I'd have candy that I'd be throwing at you. Not you. So we know that it's a key tool, and I can do some tremendous work to model for you as an expert in physics to say this is how I think about things. But it's only one tool. And we have loads and loads of data, like those data that I showed you, that say that students learn more. The students learn more in terms of conceptual measures, they learn more in terms of attitudes and belief. They learn more in terms of identity. Should I be participating in here? Can I engage in this environment? If DFW, drop, fail, withdrawal rate, is of interest to any of you, maybe the Ds, then we do know that these interactive engagement environments, these environments that create communities, reduce the drop, failure, withdrawal rate, and particularly the studio models that are approached. So we can address those. And the traditional problem solving, I didn't show these data, but if anybody wants to see, I can show you that students perform better on traditional, the end of chapter, quantitative problem solving. Those things that professors usually say, no, wait a second, I can't lose time to do X, Y, or Z. But it turns out students weren't learning that anyway. And we can demonstrate that students learn the traditional material better and all of this stuff that we really do care about but haven't externalized. So, people have studied this question, how is it that we convince people, and none of those arguments work? It's true. It's not that none of them work. People love to have data after the fact. There's a big question about what is it that convinces people. I open up my classroom, I start my classroom, I don't even have anything close to Physics 7, but I start all of my classrooms that are highly demanding of students to think differently. Again, students have come, they've been highly selective for the ability to bubble in sheets to get into the university, right? How many sheets did you bubble in to get into the University of California? Lots and lots and lots, not to mention. Anyway, so I open up the hood of the classroom and I say, let's talk a little bit about the nature of learning. I know this might be different, but let's wrestle with it. And let me know if this is not working for you, and if you have an alternative. If you can demonstrate to me that you can learn more effectively otherwise, then show me. But here are the data that I have that show that students are more active, more engaged, learn more, participate more likely to succeed through these routes. And I think that those data, so one thing I do is I open that up and I have a discussion in my classroom about it. That seems to help with the students. That, and I think there is a hugely important element to the end of semester evaluations. We call them faculty course questionnaires, but they're the evals. They matter a lot because that tells you whether or not students are going to vote with their feet. Do they like it? Do they feel like this class matters? And I want my students to say yes. I want my students to know that I care about them. I want them to know that I care about their learning. And so I make that very apparent too. So, great question, really hard to answer. We'll start over in the back there. Yeah.
Vast body of literature in learning sciences suggests that nobody learns the same material at the same speed, and the speed at which they learn it is not a very good indicator of how well they can use it. So why do we cling to the architecture of quarters and classes?
You're the ones at the agrarian institution here and taking summers off and going back to work at the farm, all right? So the question was, there's lots of evidence that people don't all learn the same way, at the same speed, in the same manner. Why is it that we have sort of this lockstep? I think that this is something that I'm really optimistic about with the advent of technology. I refuse to do away with the incredibly valuable person-to-person time that we have. But A, let's make that valuable person-to-person time. Let's not spend that time with the information delivery. Let's outsource the information delivery and sort of individual practice problem solving that we can do. We can put all of that online. I think that there's tremendous opportunity for us to do that. But the kinds of activity where students are collectively sense-making and arguing and engaging in collective negotiations is very, very valuable here, and it sets the norms about what it is that we can do. So, and then that allows for the multiplicity of ways that people engage with material and the pace with which they do so. So I think that we have the opportunity to address, including more students more effectively using technology, but not outsourcing it completely. I think that the future suggests strongly, and as well as their research, the very paltry amount of research that we have in this area of hybrid models. So I hope that's a start. That why it is as it is, I'll leave to historians and right, politicians. I defer to the dean. Yes?
Thank you. You're the only one who does. So does this discipline-based research that you do in physics and physics learning have an impact going the other way for the School of Education, their partners, and how they prepare K-12 teachers? And are there findings that demonstrate things like longevity in the field, better outcomes for students, more satisfaction, whatever?
So the question is this a bi-directional? Well, we've imported a bunch of great resources from education, psychology, and elsewhere. Does it feed back into School of Education, teacher certification? Are there impacts otherwise? And the answer is yes. Next question. No. Absolutely. So a great example of this is the learning assistant model. So the learning assistant model are students that we're looking to recruit to be future physics teachers, biology teachers, chemistry teachers. And you know, we only get 15% of those students who go into certification. The other 85% are failures who go on to graduate school in physics. And there's a little quip. The point is everybody's a teacher. Everybody is a teacher, whether formally or not. And so we are preparing people to be better educators and teachers across the board. And as a graduate student, you know that you have the opportunity, should take the opportunity to teach, but also in industry and elsewhere, we're engaging in social interaction and enterprise and enculturation of students, which is what teaching is. And so we can better do that. There's also evidence that it makes you a better learner, and so you're better able to perform in your classroom, your own learning. There. So, this learning assistant program, though, which was then where we get these students to transform these classrooms, make them more interactive, was only recently adopted back into the School of Education, where in our education classes, we'll now have learning assistants helping with the education classes themselves. And so, that's one form. The other form is, we're now seeing, as a result of the learning assistants coming in, the learning assistant program is a recruitment tool, but we have very high level of scaffolding in two ways. There's a weekly meeting with the disciplinary faculty, again, much like you do in Physics 7 with the TAs to prepare them for the upcoming recitation section. And you have the opportunity to work with them around what are student ideas, what are people going to have difficulty with, and prepare the TAs to do that. That's what we do with our learning assistants and teaching assistants in cooperation with the faculty. And then also there's a weekly seminar in the School of Ed to talk about general learning strategies and negotiating discourse and asking good questions and looking for a metacognition, whatever that is. So that preparation, that really heavy scaffolding and support, which gives people an introduction, led students to come into the School of Ed so much better prepared than students who hadn't gone through that route that we've restructured our entire teacher certification program, partly with the help of ExxonMobil through our CU Teach, our U-Teach replication program, but we've now restructured that, demanding this more or less as a precursor, that or step 1, step 2, as a precursor for engaging in our coursework, so we've changed that. Finally, the answer is to retention. The answer is yes, we see our retention rate up for teachers who go out into the field upwards of 93% over 5 years. National average is closer to 50%. So, and how we do that is that once our teachers leave, I'm a physics professor, but I meet with students who are physics teachers who came out of our program because we're part of a community together. They live nearby, and they're supporting my students who I'm recruiting to be future teachers from the physics department. And so we create this sort of recursive form of engagement, and it's a tremendous partnership now that exists between arts and sciences. I notice you guys sitting on the opposite sides of the room already, and I want you to get you together. No, but anyway, it's a tremendous partnership. Our physics department is better, our School of Education's program, and our schools are better as a result of this. Absolutely. Another question?
Are you taking any steps to ensure like a consistency of quality between learning assistants and does that make a difference?
We do it, it's very competitive. We actually hire now upwards of 200 learning assistants per semester, which is big. The provost pays for it, so you don't have to worry about it, deans.
That's there.
Yeah. Okay, well, we'll work on them. Work on them. But in terms of consistency, so it's a very competitive process. So we start students, and different departments have different metrics by which they select students. We have 60 applicants for 20 spots in physics, which is where it started. And so we generally tend to bring in students who know the material well, have performed well in the class, I should say, but they're not expected to be masters of material, they're expected to be masters of learners. of learning. So they are really good questioners. They're really good at listening to students. You're not supposed to be knowers as a learning assistant, or frankly ever as a teacher. You're supposed to be sort of an expert learner to scaffold and support students. So we see less variation. There are some variations, and it does matter, but there's much more variation, interestingly enough, among the faculty, and how the faculty frame what this activity is for their students in the classroom, as well as for what the learning assistants. So at minimum, the faculty say, all right, I want you to go through the material and learn all the material so that you can share it with others. That's the base level that we have. But the faculty have been doing this for a while, and sort of we work with to sort of coach. They start saying, this is all the material, I want you to learn it and know it, you should feel pretty comfortable, but I want you to put yourself in the shoes of a student. What are the difficulties, what are the reasoning that students are going through in making sense of this? And now, how do you respond? Now, again, professionalizing this nature of teaching. Great question. Yep.
I had a question. Right now, we've done the frameworks. We've got a math framework and a science framework, which are separate. And we don't have an engineering framework at the K-12 level. And the top achieving nation in the world is Finland, who is doing a lot of project-based learning, theoretically integrating STEM in their projects. So, and that's also very effective for the second language Danish speakers who were formerly underperforming before they started the project-based learning. So if Finland is doing so well, doing projects that presumably integrate STEM, should we be looking more closely at that to do our K-12 STEM integration rather than just approaching the two separate disciplines?
Right, so the question is should we be focusing more, particularly K-12, but I think this applies at all levels, to an integrated approach and a coherent approach across disciplines rather than saying one discipline or another discipline, think about an integrated approach across STEM? And the answer is yes and no. Next? No. So I think we have tremendous opportunity, and it really matters how we do it. So right now, the next gen science standards are on deck to be released. Colorado is dragging its feet on endorsing this as a state. The 26 states have endorsed this, say that they are going to adopt these, and I'm hoping to embarrass Colorado into that adoption. And in that, we do talk about the integration. So there's cross-cutting concepts as one of 3 major strands in this. So I think that this is an opportunity. That said, then it's incumbent upon us as teacher educators, as disciplinary experts, as future teachers, as students, to start looking for how we are going to support teachers for doing that, and how we're going to then, and those who are writing the assessments, and we have to get in the game, to effectively engage in the assessments that'll really end up driving that. So supporting teachers, having accurate good assessments, and having good curricula that does do that. So I think it's a tremendous time of opportunity. The devil's in the details, and we'll end up seeing. All right, maybe last question, I'll let y'all go. Yep.
So quick question. You said you have 20 in physics of these learning assistants, which
Yes.
is 200 that are being paid. Who else have you impacted?
Oh, yeah, so it's across 9 different departments. So I think, so we have them in biology, in math, and in applied math. We have them in astrophysics. We have them in geoscience. This is interesting, the geoscience story was driven by students. Students went and petitioned the department chair and said, we want to do this in our own. And then the department chair found a faculty member. So, so most of the science departments are engaged. So we have 9 explicit departments, and several engineering departments are starting to come on board now. If you're interested, LA program, all one word, .colorado.edu. We're in the midst of a national replication effort behind that, funded. So we're very eager to create a national sort of network behind this, as we're also interested in creating a national network around these centers for STEM learning. I think hold tremendous portent for what we can do. So, and one thing I didn't mention here, the LA program is a great model of, so I study institutional transformation. The LA program is a great example of grassroots movement growing up from the seeds, as I mentioned in that story of the geoscience students, driving, saying we want this, forcing the top-down support. And I think this is a great model of educational transformation, both in the small scale for individual students. It's what the Learning Assistant program does. It's a great where when we first launched this, we were very explicit about recruiting and preparing teachers, and we were very explicit about improving course outcomes. We were less explicit about faculty development, but we did see this as faculty development for our faculty, and we were very quiet about this as a mechanism for institutional transformation. Now we're shouting it from the rooftops. Now that other folks are coming along, we say we have a model of institutional transformation. This is one example. Another example that we have is the Science Education Initiative in Colorado and the Center for STEM Learning. All of these follow this idea of saying, let's take this grassroots effort here, because that's where change happens. Let's take a departmental level focus, and let's support it then institutionally for the long-term welfare of our institution. Oh, okay, we have a couple more questions. We have time for, okay.
This isn't a question, but just a point of information for those here. We do actually have a small LA program here, modeled after yours, yes, in both physics and bio-sci, and looking to expand that program. So those of you who are going, yes, we should be doing this, well, please, yes, talk to us. We need to do it. Okay.
I had a quick
Yep.
As an undergrad here, I would work a lot for extra units. So do you think instead of paying students, would it be for credit? Would that work as well?
Yes. So I actually, a proto version or a pre-version of Learning Assistant programs, I have a class that I call Teaching to Learn Physics. And so there's a fieldwork component in the physics class as part of the restricted electives for the majors in physics, where students get to learn about PER and teaching, and they as part of their course credit. So your question is, instead of getting paid, can I pay through tuition in order for this honor? And the answer is, of course we'll take your money. And that's what we have to do.
I guess I should have mentioned that that's what happens here. You get credits.
Other questions? Yeah?
As you know, there is a lot of attention recently to the concept of college and career readiness. In the new standards, the Common Core Study standards, there is a lot of requirement and attention to this. And because you mentioned about assessment, in the assessment there are, as you know, 2 consortia of states with huge amount of money fund to create assessment, and they are paying attention to college and career readiness.
Right.
Now, my question to you is that if you pay attention, would that prepare the students more to be educational physics researchers?
If we prepare students earlier,
exactly.
Right, through career readiness, would they come to the university then to be ready?
To be a good, better researcher.
Yes, I think, if I get your question right, which is to say, if we really focus students to be college and career ready, are they better prepared to be a researcher? And in my book, physics education research is just one discipline of the many subdisciplines of physics we engage in. And I think that we're now in this position to treat this in a really scholarly way. So I think that I would love, I mean, maybe this is a subset of a broader response, which is I would love for us to be able to achieve these standards that we have in college and career readiness. It would be amazing to me if students arrived at the university with the support that is outlined or implied by these sort of national standards and these college and career readiness standards. So I think that this is something that it's essential that we engage in. In terms of the measures of this, I'm unaware of those measures being based on research within the disciplines. And so this is something that we must engage in. Oh, we keep coming, yeah.
Just wondering, in your program, do online resources play any important role?
In my program, do online resources play any important role? Yes. So I think that we have to engage, I think that this is a really ripe time to be studying, and we should be using the opportunity and pressure for online education to be studying learning outcomes overall and to be able to prepare this. And this is a new opportunity for us. So never let a good crisis go to waste. There's this freight train coming here in online education that's running straight at the university. And between that and sort of these pressures for efficiency, we have the opportunity for us to, on the one hand, define the learning outcomes and objectives and successes that we are engaged in. And then the other is to utilize technology. I have a whole other talk on this that I'm happy to send you. But it plays to this idea, technology, you know, the new technologies, those are just another tool that go in that little toy framework. And we could talk about what they do and what they don't do for us. So yes, we use technology all the time. We build computer simulations. If anybody wants the PhET interactive computer simulations, phet.colorado.edu. They get 35 million downloads a year. They're in 77 different languages. We have 105 computer simulations in math, physics, chemistry, biology, and we're expanding them. They're free. They're fun. I have 5-year-olds doing Fourier decomposition in coffee shops when I hang out there because they get to play and learn. We can demonstrate. Those are incredibly powerful tools for teaching in a new way and providing accessibility. Just like you change from 5 fingers to 8 fingers on each hand, we now provide people new tools to think about and engage in the world in new ways with these simulations. And I think that we are just at the beginning of this, provided that we're clever and thoughtful about it, and notice what they can and cannot do. So I will then thank you all so much and defer to one of my tremendous hosts.
We're going to hijack for just a moment because we don't want to let this opportunity go to waste. But there may be some folks in the room who want to get connected from various departments on campus into more of a community that could start to engage in these questions more systematically, crossing both the School of Education and discipline departments. And so Marco's hijacking Noah's computer in order to put our email addresses up there. So Marco is heading out to IM STEM Hub, which is trying to coordinate and synthesize the work on this campus around these kinds of questions. And so he has more. And then, so anyway, we're putting our email addresses up, so feel free to contact either Marco or myself about your interest in these areas, and then I will turn it over to our dean to give the final benediction. Should be pass mark. There we go.
Thank you. Well, I just want to thank you all for coming and appreciate the interest in this talk. As Cindy said, we are very eager to have continued dialogue between the sciences and the School of Education and to try and enrich our curriculum and our teacher preparation program and our undergraduate science classes in many of the same ways that Noah has talked about. This is a big STEM campus. There's a lot of stuff going on here. We'd like STEM education to be front and center of a lot of our activities. And by the way, for those of you who are undergraduates, if you are interested in a career in teaching in physics or some other science, we have people outside. No, we'd love to have you come and explore. We want more of you who have real disciplinary knowledge to come to our program. And in fact, our Director of Teacher Education, Chris Faltis, is here. And we'll be happy to answer any of your questions. Let me also thank again the Graduate Group in Education for co-sponsoring this along with the School of Education Alumni Annual Fund, and of course our great friends Dean Code in Mathematical and Physical Sciences and Andy Albright from the Department of Physics. So thank you all. Noah, thank you for being here. I've been looking forward to this. We talked last spring about Noah coming to our STEM Summit on campus. He was unable to come because he was in some important place like IPC, I think, at the time. But I'm glad you could come to this. I'm really thrilled. And I know you've stimulated a lot of interest here. And of course, we're all jealous of what you've been able to accomplish in Colorado. This is a little parting. In addition to our thanks, this is a little parting gift. This is UC Davis olive oil. I don't know how many of you know the story about our olive oil, but in addition to education and physics and STEM education, we're also known for olive oil and wine too, by the way. The university for many years, well, there's 100-year-old olive trees all over the campus, and for many years there were countless lawsuits for bicyclists and others who fell over the olives that had fallen to the ground, and thousands and thousands of dollars to clean up the mess. So a groundskeeper one day looked at those olives and he thought, olive oil. And sure enough, here it is. So we present this to you, and our thanks for being here.
Thank you.
Thank you all for coming. Good night.